Yes, it is indeed true that opening the main power to a motor can cause overcurrents and subsequent damage to the fuses. Let's delve into the reasons why this occurs. When a motor is actively connected to a power source, it establishes a magnetic field. This magnetic field is fundamental to the motor's operation, enabling it to convert electrical energy into mechanical energy. However, when the power supply is abruptly cut off, this established magnetic field doesn't simply vanish instantaneously. Instead, it collapses. This collapse of the magnetic field is the root cause of the phenomenon we're discussing. The collapsing magnetic field induces a high voltage within the motor windings. This induced voltage is known as the back-electromotive force, often abbreviated as BEMF. The BEMF is essentially a voltage that opposes the change in current that caused it. In this case, the change in current is the abrupt cessation of power to the motor. Now, this BEMF can cause substantial currents to flow through the motor's internal circuitry. These currents can exceed the normal operating current of the motor, leading to an overcurrent situation. It's crucial to understand that this overcurrent can damage the fuses, even if the fuses are nominally rated to handle the motor's typical running current. The fuses are designed to protect the motor and the electrical system from sustained overcurrents, but the rapid and intense surge caused by the collapsing magnetic field can overwhelm them. The extent of the overcurrents generated during this event is not a fixed value. It varies depending on several key factors. Firstly, the size of the motor plays a significant role. Larger motors, naturally, have larger magnetic fields, and a collapse of these larger fields will induce higher BEMF and consequently, larger overcurrents. Secondly, the type of motor is a determining factor. Different motor types, such as induction motors, synchronous motors, and direct current motors, have different electrical characteristics and respond differently to the sudden interruption of power. Thirdly, the speed at which the power is interrupted is critical. A rapid interruption, such as that caused by a shunt switch, will result in a much higher BEMF and more severe overcurrents compared to a gradual power down. Fourthly, the presence of any additional inductive loads in the circuit can exacerbate the problem. Inductive loads store energy in a magnetic field, and when the power is cut off, this energy can be released, contributing to the overcurrent. In the specific situation involving the marquee, the shunt switch likely caused a very rapid interruption of power to the motor. This rapid interruption would have induced a substantial BEMF, which in turn could have caused the observed damage to the fuses. It's important to recognize that the damage to the fuses may not always be immediately apparent. The fuses may continue to function for a period of time after the event, but their internal semiconducting material could have been partially compromised. This partial damage means that the fuses will be more susceptible to blowing at a lower current level during the next high current event. To further enhance your understanding of motor collapsing fields and overcurrents, I recommend consulting the following resources. Firstly, explore the concept of back-electromotive force in motors. The site Electronics Tutorials. WS provides a comprehensive explanation of this phenomenon. Secondly, delve into the topic of overcurrent protection for motors. The website electricafaru.com offers valuable insights into the methods and techniques used to protect motors from overcurrent conditions. Thirdly, examine the specific issue of motor overcurrent protection. The website omega.com provides detailed information on this subject. Now, let's discuss some practical considerations for mitigating the risk of overcurrents caused by motor collapsing fields. Firstly, consider using soft starters or variable frequency drives, often abbreviated as volts, to gradually start and stop motors. These devices control the voltage and frequency applied to the motor, reducing the inrush current during startup and minimizing the BEMF during shutdown. Secondly, incorporate surge protection devices, often abbreviated as volts, in the motor circuit. These devices can help to absorb the high voltage surges caused by the collapsing magnetic field, protecting the fuses and other components from damage. Thirdly, ensure that the fuses used in the motor circuit are properly sized and rated for the application. Consult the National Electrical Code, often abbreviated as NEC, and other relevant standards to determine the appropriate fuse size. NEC Table 430.52 provides guidance on motor overcurrent protection. Consider using time delay fuses, which are designed to withstand temporary overloads without blowing. Fourthly, implement a controlled shutdown procedure for the motor. Instead of simply throwing a shunt switch, consider using a controlled stop function that gradually reduces the motor's speed before disconnecting power. This will minimize the BEMF and reduce the risk of overcurrents. Fifthly, regularly inspect and test the fuses in the motor circuit. Look for any signs of damage or deterioration, such as discoloration or cracks. Replace any suspect fuses immediately. Sixthly, consider using a motor protection relay, often abbreviated as VoltSpur. This device monitors the motor's current, voltage, and temperature, and it can detect overcurrent conditions and other faults. If a fault is detected, the motor protection relay will automatically trip the circuit breaker, protecting the motor from damage. Seventhly, implement a robust grounding system. A properly grounded system provides a low impedance path for fault currents to flow, helping to protect equipment and personnel from electrical hazards. Eighthly, consult with a qualified electrical engineer to assess the specific needs of your application and to design an appropriate overcurrent protection scheme. Ninthly, provide adequate ventilation for the motor. Overheating can exacerbate the effects of overcurrents, so it's important to ensure that the motor is properly cooled. Tenthly, keep the motor clean and free of debris. Dirt and dust can insulate the motor windings, preventing them from dissipating heat effectively. These measures will significantly reduce the likelihood of fuse damage and extend the life of your motor. Let's delve deeper into the specifics of fuse selection for motor protection. It's crucial to choose fuses that are specifically designed for motor protection applications. These fuses typically have a time delay characteristic that allows them to withstand the temporary high inrush currents that occur during motor startup without blowing. There are several types of fuses commonly used for motor protection, including dual-element time delay fuses, often referred to as Class CC fuses, and R-cone fuses. Dual-element fuses have two separate elements. One element provides overload protection, while the other provides short-circuit protection. Class CC fuses are compact and current-limiting, providing excellent protection against both overloads and short circuits. R-cone fuses are also current-limiting and offer a high degree of protection. When selecting fuses, it's essential to consider the motor's full load current, service factor, and starting current. The full load current is the current the motor draws when operating at its rated horsepower and voltage. The service factor is a multiplier that indicates the motor's ability to handle occasional overloads. The starting current is the current the motor draws during startup, which can be several times higher than the full load current. To determine the appropriate fuse size, consult the NEC, specifically Article 430. This article provides detailed guidelines for motor circuit protection. In general, a fuse size should not exceed 175% of the motor's full load current for inverse time circuit breakers or 225% for time delay fuses, as per NEC Table 430.52. It's also important to consider the ambient temperature in which the fuses will be operating. Fuses are sensitive to temperature, and their current carrying capacity decreases as the temperature increases. If the fuses will be operating in a high-temperature environment, it may be necessary to derate them accordingly. In addition to fuses, circuit breakers are also commonly used for motor protection. Circuit breakers provide similar protection to fuses, but they can be reset after they trip, whereas fuses must be replaced. There are several types of circuit breakers suitable for motor protection, including inverse time circuit breakers and instantaneous trip circuit breakers. Inverse time circuit breakers trip faster as the current increases, providing overload protection. Instantaneous trip circuit breakers trip very quickly in response to a short circuit, providing short circuit protection. When selecting circuit breakers, it's essential to consider the motor's full load current, service factor, and starting current, just as with fuses. The circuit breaker's trip current should be set to a value that is high enough to allow the motor to start without tripping, but low enough to provide adequate overload protection. NEC Article 430 provides detailed guidelines for setting the trip current of circuit breakers. It's also important to consider the circuit breaker's interrupting rating, which is the maximum current that the circuit breaker can safely interrupt. The interrupting rating should be high enough to handle the potential fault current at the installation location. Remember, proper motor protection is essential for ensuring the safe and reliable operation of electrical equipment. By understanding the principles of motor collapsing fields, overcurrents, and fuse selection, you can significantly reduce the risk of equipment damage and downtime. Let's explore the phenomenon of back-electromotive force (BEMF) in greater detail. As previously mentioned, BEMF is the voltage induced in a motor's windings when the magnetic field collapses or changes. This phenomenon is the direct consequence of Faraday's law of induction, which states that a changing magnetic field induces a voltage in a conductor. In the case of a motor, the rotating rotor generates a magnetic field that interacts with the stator windings. This interaction induces a voltage in the stator windings that opposes the applied voltage. This opposing voltage is the BEMF. The magnitude of the BEMF is proportional to the motor's speed and the strength of the magnetic field. As the motor's speed increases, the BEMF also increases. Similarly, as the magnetic field strength increases, the BEMF also increases. When the motor is running at a constant speed, the BEMF is nearly equal to the applied voltage. This means that the net voltage across the motor's windings is relatively small, resulting in a relatively small current flow. However, when the motor's speed changes rapidly, the BEMF also changes rapidly. This rapid change in BEMF can induce large currents in the motor's windings. For example, when the motor is suddenly stopped, the magnetic field collapses rapidly, inducing a large BEMF. This BEMF can cause a surge of current to flow through the motor's windings, potentially damaging the fuses or other components. The BEMF can also be a factor in motor starting. When the motor is initially started, the rotor is stationary and the BEMF is zero. This means that the full applied voltage is across the motor's windings, resulting in a large inrush current. As the motor speeds up, the BEMF increases, reducing the net voltage across the windings and limiting the current. The magnitude of the inrush current can be several times higher than the motor's full load current. This high inrush current can cause voltage dips in the electrical system and can also stress the motor's windings. To mitigate the effects of BEMF, various techniques are employed, such as using soft starters or variable frequency drives, as previously discussed. These devices gradually increase the voltage applied to the motor during startup, limiting the inrush current and reducing the stress in the motor's windings. They also control the rate at which the motor slows down during shutdown, minimizing the BEMF and reducing the risk of overcurrents. Another technique is to use a braking resistor. A braking resistor is connected across the motor's windings during braking. When the motor is decelerating, the BEMF generates current that flows through the braking resistor, dissipating the energy as heat. This helps to slow the motor down quickly and smoothly without generating excessive BEMF. Let's turn our attention to the topic of inductive loads. As mentioned earlier, inductive loads store energy in a magnetic field. Examples of inductive loads include motors, transformers, and inductors. When the current flowing through an inductive load is interrupted, the magnetic field collapses, releasing the stored energy. This release of energy can induce a voltage surge, which can damage sensitive electronic equipment. The magnitude of the voltage surge depends on the inductance of the load and the rate at which the current is interrupted. The higher the inductance and the faster the current is interrupted, the larger the voltage surge. To protect against voltage surges caused by inductive loads, various surge suppression devices are used. These devices are designed to absorb the excess energy and limit the voltage to a safe level. One common type of surge suppression device is a metal oxide varstor, often abbreviated as MOV. MOV is a voltage-dependent resistor that has a high resistance at normal voltages but a low resistance at high voltages. When a voltage surge occurs, the MOV resistance drops, diverting the surge current away from sensitive equipment. Another type of surge suppression device is a transient voltage suppression diode, often abbreviated as TVS diode. A TVS diode is a semiconductor device that clamps the voltage to a specific level. When the voltage exceeds the clamping voltage, the TVS diode conducts, diverting the surge current away from sensitive equipment. Surge suppression devices are typically installed in parallel with the inductive load that is generating the surge. This allows the surge suppression device to absorb the excess energy and limit the voltage to a safe level. In addition to surge suppression devices, other techniques can be used to mitigate the effects of inductive loads. For example, snubbers are often used in circuits with inductive loads. A snubber is a network of resistors and capacitors that is connected in parallel with the inductive load. The snubber helps to damp out oscillations and reduce voltage surges. Another technique is to use a freewheeling diode. A freewheeling diode is connected in parallel with the inductive load, with the cathode connected to the positive side of the power supply and the anode connected to the negative side. When the current through the inductive load is interrupted, the freewheeling diode provides a path for the current to flow, preventing a voltage surge. Understanding the behavior of inductive loads and the techniques for mitigating their effects is essential for designing reliable and safe electrical systems. It is important to consider the potential for voltage surges and to implement appropriate surge protection measures to protect sensitive electronic equipment. Let's explore some additional factors that can affect motor overcurrent protection. One important factor is the altitude at which the motor is operating. At higher altitudes, the air is less dense, which reduces the motor's cooling capacity. This can lead to overheating, which can exacerbate the effects of overcurrents. If a motor is operating at a high altitude, it may be necessary to derate it or to provide additional cooling. Another factor is the ambient temperature. As mentioned earlier, fuses and circuit breakers are sensitive to temperature. If the ambient temperature is high, it may be necessary to derate the overcurrent protection devices. Additionally, the presence of harmonics in the electrical system can affect motor overcurrent protection. Harmonics are distortions of the sinusoidal waveform of the alternating current power supply. Harmonics can cause increased heating in the motor windings, which can lead to premature failure. If harmonics are present in the electrical system, it may be necessary to use harmonic filters to reduce the harmonic content. Furthermore, the type of load that the motor is driving can affect overcurrent protection. For example, if the motor is driving a high inertia load, such as a flywheel, it will take longer for the motor to accelerate to its rated speed. This can result in a prolonged period of high current, which can trip the overcurrent protection devices. In such cases, it may be necessary to use time delay fuses or circuit breakers to allow the motor to start without tripping. The condition of the motor's insulation is also a critical factor. Deteriorated insulation can lead to ground faults or short circuits, which can cause overcurrents. Regular insulation testing is essential for detecting insulation problems before they lead to major failures. Finally, proper maintenance of the motor and the electrical system is essential for ensuring reliable overcurrent protection. This includes regular cleaning, lubrication, and inspection of the motor, as well as regular testing of the overcurrent protection devices. By paying attention to these factors, you can improve the reliability of motor overcurrent protection and prevent costly equipment failures.